Hello, everyone. My name is Xiaotong Liu. I'm a research scientist from IBM Research Almaden. Today, I'm going to present our paper using language models to pre-train features for optimizing information technology operations management tasks. IT operations environment generate many kinds of data. These include metrics, alerts, events, logs, tickets, application and infrastructure topology, deployment configurations, and chat conversations. Of these, metrics and alerts tend to be structured in nature, where logs and tickets are unstructured data types. Also among these data types, logs and metrics sometimes can be leading indicators of problems, while alerts, tickets, and chat conversations turn to be lagging indicators. As IT complexity grows and the use of AI technologies expands, enterprises are looking to bring in the power of AI to transform how they develop, deploy, and operate their IT. The volume, the variety, and the complexity of these data offers both challenges and opportunities in developing AI-infused analytical tools to optimize IT operations management tasks. Embeddings, also known as distributed vector representations, have been widely used in natural language processing and natural language understanding. In the pre-trained embedding space, words or phrases from the vocabulary are mapped to vectors of real numbers, and each is associated with a feature vector of a fixed dimension. Embeddings are pre-trained on large text corpus using a language modeling task, which assigns a probability distribution over sequences of words that matches the distribution of a language. After that, embeddings can be extracted from the pre-trained language model. And typically, we can categorize embeddings into two types based on the language modeling approach in use: context-free embeddings and contextualized embeddings. Static word embeddings, context-free, as the language models generate the same embedding for the same word even in different contexts. The examples are fast text, word-to-vect, and glove embeddings. Deep pre-trained language models such as BERT, Elmo, Elfid can generate contextualized embeddings, while the representation of a word also depends on the other words in a sequence. So that is the context of the word. And for the scope of this work, we select two representative embeddings from each type, and fast text for context-free embeddings and BERT for contextualized embedding. To support IT operations, many AI pipelines can be designed and developed to process different types of data and generate insights from them. For example, application and infrastructure logs and metrics are parsed and processed to predict anomaly early in the process. These are handled by log anomaly and metric anomaly prediction models. Anomalies that are raised in other events and alerts that may be generated by rules are then grouped into their corresponding incident buckets by leveraging various techniques, including entity linking and spatial temporal and topological algorithms to reduce event noise. This is done by event grouping AI models. Faults are diagnosed and localized by fault localization AI models. The set of impacted components are noted by blast radius AI models. Similar incidents from the past incident records are identified, and next best action can be derived by incident similarity AI service. Each one is an AI model that employs different algorithms. Some are deep learning algorithms, and some are unsupervised machine learning algorithms. The features used in all these models could benefit from a deeper understanding of IT domain. Leveraging language models to pre-train features from IT operations domain data, we present a transfer learning approach that serves as a strong foundation to build AI models for various different IT operations management tasks. Most existing embeddings available in the literature were created from text corpus in natural language, such as Wikipedia pages and news articles. However, the text data generated in the IT operations domain are very different from natural language text, as the vocabulary of the IT operations domain is quite unique. To pre-train language models in the IT operations domain, we first process the input IT data into a normalized format using predefined rules, extracting the most informative texts, such as log messages, ticket descriptions, and so on. We also remove duplicates of text, which may be auto-generated multiple times by the system for the same event. Next, we randomly sample data from each data source and use the data samples to learn the vocabulary of the IT operations domain. After that, we pre-train the language model using the sample data and tune the parameters based on model evaluation. To demonstrate the feasibility of our approach, we describe a case study of using language models to pre-train features for building log anomaly detection and prediction models in IT operations management. We develop a system to perform anomaly detection and prediction based on pre-trained features from language models. Our system consists of two subsystems: offline training and runtime inference. The offline training subsystem focuses on log parsing, embedding extraction, and log anomaly detector training. The input to this subsystem are random sample log data and a pre-trained language model, such as fasttext or BERT. We generate a vector representation from each log message. From fasttext embeddings, we aggregate the embeddings from the words in a sentence using TF-IDF weighting. From the pre-trained BERT model, we take its final hidden state of the token CLS as the aggregated sequence representation. To model the system behavior over time, we group the log messages of every 10-second time window based on the login timestamp, and aggregate the vectors of logs within each time window to form the feature vector. We learn a principal component analysis transformation matrix from feature vectors in training data collected when the system was running in normal condition. The output of this subsystem are trained log anomaly detector models, which are saved to the storage repository data lake. The runtime inference subsystem checks if an anomaly occurs for a given time window during runtime. The input to this subsystem are the trained models from the offline training subsystem in the data lake, as well as new logs in a streaming fashion through Kafka data streams. Our system will predict anomaly if the feature vector of a new time window is sufficiently different from the normal space constructed by PCA. The output of this subsystem continuously are anomaly detectors detected from logs, so the feedback on the anomaly detection results will be used to improve the offline training subsystem. In our experiments, we tested whether anomaly detection models built with features derived from word embeddings from the language models trained on IT data outperform the ones that are built with the general purpose technologies. In particular, we explored the effects of three factors that may affect language model pre-training for IT operations management: the types of language models, the types of pre-trained data, and the diversity of pre-trained data. For pre-training the language models, we take 3 million sample logs from a large number of applications. To test the accuracy of our trained anomaly detection models, we collect logs with ground truths from 2 IBM Watson Assistant microservices when the system was running in normal or abnormal condition, along with the HDFS ground truth data from log.hub. We compare the predictions with ground truth and compute the per-class accuracy as the percentage of correct predictions to normal or abnormal test data set. So we train several anomaly detection models using different pre-trained features. Our baseline uses comp vectors of log templates as the feature vectors to build the model. The fast-text origin model was built using features from the original pre-trained fast-text embedding using general-purpose data. The fast-text AA model was built using features from our fast-text embedding pre-trained using IBM Watson Assistant data. The fast-text AA and log.hub model was built using features from our fast-text embedding pre-trained using IBM Watson Assistant and log.hub data. And similarly, we have 3 versions of models for BERT models: the BERT origin, BERT AA, BERT AA log.hub models. Here we report the accuracy results of anomaly predictions on the benchmark datasets across various models. Firstly, we can see that the models trained with context-free embeddings consistently outperform our baseline, as well as the models trained with contextualized embeddings. Where our pre-trained fast-text embedding using the Watson Assistant data is comparable to the original general-purpose fast-text embedding, we get a significant boost in accuracy of 8% with our pre-trained fast-text embedding using both the Watson Assistant data and the log.hub data, compared with the general-purpose fast-text embeddings. This demonstrates the effectiveness of using diversified domain-specific data for pre-training embeddings to enhance log anomaly detection task. On the other hand, we can see that our pre-trained BERT embedding with the Watson Assistant data is also comparable to the original general-purpose BERT embedding, although both are slightly worse than the baseline. Surprisingly, when we introduce more diverse data from both the Watson Assistant data and the log.hub data to pre-train BERT, the accuracy drops considerably. One possible reason is that log data are much simpler than the general-purpose text data, such as Wikipedia articles or news articles. And the context in log data is not rich enough for BERT to learn during model pre-training. Besides, since log anomaly detection is essentially an unsupervised learning task, it is difficult to fine-tune pre-trained BERT models as in supervised learning tasks. Overall, our experiments show that context-free embeddings are more robust and effective than contextualized embeddings to pre-train features for the log anomaly detection task. And it is even better when pre-training the embeddings with the IT operations domain data of diverse applications. To conclude my talk, pre-training a language model can accelerate the development of text-based AI models for optimizing IT operations management tasks at a large scale. We investigate the effects of this language modeling pre-training approach for IT operations management through a series of experiments on different language model types, data domains, and data diversities. We present the empirical results on the prediction accuracy of our log anomaly prediction model using language models as features in the IT operations production environment. We show that In machine learning models built using context-free embeddings, trained with diverse IT operations domains data, its features outperform those AI models built using language models with general-purpose data. We hope that the insights gained from these experiments will help researchers and practitioners develop solutions and tools that enable better scalability, integrations, and management in the IT operations domain. In the future, we will continue to explore the effects of pre-trained features using language models on different IT operations management tasks, such as fault localization and similar incident analysis. Thank you for your attention. That's all.